Let's go with electrostatics of conductors. Electrical conductors has large number of mobile charges. In case of conductors, these mobile charges are free electrons. In conductors, these free electrons are not bound to any of an atom, so that they will be in continuous random motion in different directions. So there will be no net current inside the conductor. This state we call that as electrostatic equilibrium of conductors. These free electrons are responsible for conduction in a conductor. So these electrostatic equilibrium in conductors possess four properties. Let us see one by one. The first property is that the electric field is zero everywhere inside the conductor. Either it can be a hollow conductor or solid conductor. Second property, the total net charge is zero inside the conductor. So which gives us an idea that the charges always resides on the surface of the conductor. Inside the conductor, the total net charge is zero, which means that there is no electric field. Is that when we take a point outside the conductor, so that the electric field outside is perpendicular to the surface area of the conductor, and whose magnitude will be sigma by epsilon naught. We already know that sigma is nothing but surface charge density. And the fourth property, the equipotential on the surface and the equipotential inside the conductor will always be same, which means that the conductor is in equipotential, or we can say that the conductor is in electrostatic equilibrium. Using Gauss law, we proved that electric field inside the conductor is always zero. This property holds some important consequences. Consider a conductor possesses some cavity. Inside the cavity, let us place some conducting material. So whatever charges on the surface or whatever electrical disturbances outside, it does not affect the conducting material which is kept inside the cavity, because as it said before, electric field inside the conductor is zero. So this property is known as electrostatic shielding. This property is explained by Faraday cage. Next is electrostatic induction. Electrostatic induction is a technique of charging a conductor. So in this case of electrostatic induction, the charging is done without actual contact. So this is the one method of charging a conductor without actual contact. Okay, let us understand electrostatic induction with an experiment. So for this, let us consider a sphere which is neutrally charged, or we can say that it is in electrostatic equilibrium, and all the positive and negative charges are spread across the sphere uniformly. Now we are bringing a negatively charged rod closer to the sphere, such that the positive charges in the sphere are attracted closer to the negatively charged rod, and the negative charges of the sphere are repelled to the other side of a sphere, such that the positive charge will be in one area and the negative charge will be in another area of a sphere. And now to this sphere, we are connecting the negatively charged to grounded, which means that the negative charges are transferred to the ground. We know that ground is a good receiver. The positive charges are not being transferred to the ground because the positive charges are attracted by the negative charge. which means that we are completely removing the negative charges from the sphere. Finally, when we remove the negatively charged rod, so now we can see that only positive charges are in this. So these positive charges will be distributed uniformly all around the sphere. So now we can say that the neutrally charged sphere is now becomes positively charged. Next is electrostatics of dielectrics. Dielectrics are non-conducting materials. In dielectrics there are no free electrons, and dielectrics are also known as insulators. So these dielectrics are either can be a polar molecule or non-polar molecule. First let us discuss about non-polar molecules. In non-polar molecules, both the positive and the negative charges coincide at the center. So which means that there is no permanent electric dipole moment. When an external electric field is being applied, these charges are separated by a very small distance so that they become electric dipole moment. And now we can say that this atom is being polarized and the direction will be along the electric field direction. So this we call it as non-polar molecules of. Let us take a dielectric medium where the positive charges and the negative charges are separated in the absence of electric field, and they will be in random motion such that there is no net charge inside the dielectric medium. When an external electric field is being induced, so let us take one is fully of positively charged, in another side let us take it is fully of negatively charged. So when an external electric field is applied, so these random charges will be aligned in particular way that the negative charges will be near the positive terminal and the positive charges will be near the negative terminal. So this we call it as non-polar molecules of dielectrics. So from the diagram we can see that the negative charges are near the positive terminal and the positive charges are near the negative terminal. So in the cases that is in polar and non-polar, we are by applying external electric field, we can make the dielectric to be a polarized atom. So polarization is defined as total dipole moment in unit volume of dielectric, which is given as P vector is equal to electric susceptibility into external electric field. This E is known as electric susceptibility, which is a constant.